Here are some quick notes on random walk to accompany Chapter 3 of To Build a Star. So let's just consider one-dimensional random walk, and let's take a simplest kind of situation we can imagine so that we can get a better handle of what's going on here. Okay, so we're going to take some object. Let's just take this circle. It's on a number line, and it's going to take some number of steps. And for each step, it can either go right 1 unit or left 1 unit. And the probability of going right or left is equal. So 50-50 chance of going either way. It can only go 1 unit. And it's going to take some number of hops. And its path, for instance, could look like something traced by the gray line, where let's say you happen to randomly take 2 steps to the right, and then you randomly take 3 steps to the left, and then at the end, after these 5 steps, you wind up here at position -1. Okay, so this is a random hopper, for instance. So then the average distance that we've traveled after some number n hops is just going to be equal to the average of the sum of the steps that you take. I'm going to say the steps are delta x, so that's plus or minus 1. And the average of the sum is equal to the sum of the averages, right? But your probability of going left or right for any given step, it's 50-50, right? So on average, your distance is going to be 0. So that's not a terribly useful metric, right? If we try to say how far have you traveled on average, we just get 0, which doesn't help us. So instead, let's consider the magnitude of the distance traveled, some kind of measure of that. So if we take the distance squared, then we're always going to wind up with a positive number. And that'll give us a better feel for how far away from the center of our distribution, or how far from 0 on the number line, we can have traveled after some number of steps. Because on average, you are going to wind up back at the origin, but much of the time you're not. Okay, so if we take the distance traveled, then the average distance traveled is going to be the average of the sum of these steps squared. And we can break this out into the sum of the steps times the sum of the steps. And this is then going to be equal to the sum of the steps squared, so the average step size squared, plus 2 times the sum over the average of step 1 times step 2. Okay, so we're just expanding this product here, and we're using that usual rule that the sum of the averages, the sum of the averages is equal to the average of the sum, that rule. Okay, so we've done that expansion, and now let's consider the fact that for each of these steps, you're either going to have a step going in the positive direction or the negative, so either +1 or -1, and in either case, that number squared is just equal to 1. Okay, so we know that these first ones here, that delta x squared is always going to be 1. Now what about this delta xi times delta xj? So here, again, this is the step that you take at step number I, and this is the step that you take at step number j. So these are independent of each other. Because they're independent, and each one could have been +1 or -1 with equal probability, then your average over these is going to be 0, right? Because you can think of all the combinations you can have. You could have +1 +1, +1 -1, -1 +1, or -1 -1. You take the average of that, that is going to be equal to 0. Okay, so then this average of the distance squared is just equal to the first term. All of these ones are equal to 1, and so you're just summing from step size 1 up to step size n of 1, so that average distance squared is just going to be equal to the number of steps you took. And this is for unit step size, so our step sizes are ±1. So then the average sort of positive distance that you've traveled from the origin, you can just take the square root of this distance squared, this average distance squared, and that then is going to be equal to the square root of n for our step size 1. If instead our average step size is some mean free path L, then the distance that we've traveled is typically going to be something like the mean free path L times the square root of the number of steps that you've taken. And that's something that we stated as a fact last time in the quick notes on photon diffusion, and now you've seen roughly where that square root of n comes from. So you could go ahead and use this to then calculate the photon diffusion. It turns out doing this in 3 dimensions is quite a bit more involved, and you can, at your leisure, if you want, go look at this old paper from Chandrasekhar where he does this in 3 dimensions. And you see in 3 dimensions the square root of our average distance squared, which he uses in r because it's the radial coordinate of the radial dimension, is equal to your average mean free path, because here he considers the case where the mean free path can vary, times the square root of 1/3 times n. So this is a factor of 0.6 times that answer. So for many pages of work, you get the same order of magnitude and a slight correction, which is kind of amazing. And again, you could use this to calculate the photon diffusion time, and this is in fact what was used in the calculation results that were shown in the quick notes on photon diffusion. Okay, so now you've seen 2 ways to get the photon diffusion time. There's the hand wavy one from the previous quick notes on photon diffusion combined with the previous slide that we just talked about for the random walk in 1 dimension. And then there's a third way that you see in the book, and it relies on the binomial distribution being invoked for random walk in 1 dimension. So let's just see sort of where the binomial distribution comes from. Okay, so we have our same scenario. We've taken n total steps, and m of these have been to the right. So then by definition, n minus m must have been to the left. And we're going to say the probability for any one step of going to the right is p sub r. So then, because you're either going right or left, the probability of going to the left is 1 minus p sub r. Okay. So if we want the probability for a given sequence of steps that has m steps to the right and then n minus m to the left, then for each step, we're going to have, for each rightward step, we're going to have the probability p sub r. So then if I have m steps to the right, I'm going to do p sub r multiplied by itself m times. So that's why you then get the probability of the right raised to this exponent, the number of steps you took. And the same thing for the number of steps to the left is you'd take the probability for each leftward step and you'd multiply that, or you multiply that by itself for the number of leftward steps you have. So instead you can compress that into the probability of a leftward step raised to this exponent, which is the number of leftward steps you have. But this is for a given sequence of steps, okay, where for instance you went right, right, left, left, or something like that. But you could have wound up in the same place in that case if you went left, left, right, right. So how many different ways then can we wind up with m rightward steps overall? Okay, so we have n total steps, and m of them wound up being to the right. So this is a so-called n choose m problem in combinatorics. And usually it's stated as an n choose k problem, but whatever, k is an integer. Here we're calling it m. And you have maybe worked this out in the past in a math class, or you can look this up online or in a math textbook. The solution of an n choose m problem is given by the so-called binomial coefficient. And so that is equal to the factorial of the number of steps divided by the factorial of m here, number of rightward steps, times n minus m, which here is the number of leftward steps. So that is your binomial coefficient. So you have this many combinations will wind up with m rightward steps. And for a given sequence of events, this is your probability for winding up with m rightward steps. So you take the product of these two then to figure out the probability of having m rightward steps after n total number of steps if for a given step the probability of going right is given by p sub r. So we're just taking the product of our binomial coefficient times this product of probabilities that we worked out here. And so this function here, if you want to call it that, because it kind of is known as the binomial distribution. And here's an example from the book. It's the binomial distribution plotted for 100 steps. And it's normalized so that you have a probability of 1. It's not really probability. It's some normalized probability of being 1 is you wind up at the origin. So sure, for a random walk, on average, you're going to wind up going nowhere. But what's the probability of taking 10 steps? Okay, so 10 net steps to the right. The probability of 10 net steps to the right is something like 5–10% on the order of that. And so what this means is if you have 10 net steps to the right, that would have been, for this 100-step situation, that would have been ultimately going 55 steps right and 45 left, and so then your net is a +10 to the right. Okay, and there's many different ways you could have done that. So this binomial distribution, if you plugged in the number 100 here and for capital N, and you plugged in the number 10 here for lowercase m, and if you said the probability of going right is 0.5 for any given step, then you'd solve that and you'd find a number that's in this 5–10% region. So that's just the plotting of that binomial distribution. So then for a given average m, what's the average m that you get for this distribution? It's your total number of steps times the probability of going right. And then the variance of the distribution, so that's sort of a measure of the spread, right? The square root of the variance is known as sigma, and 2.35 times sigma is the full width at half max. So then your variance of the distribution is given here, and you work out in the homework how to use this information to again calculate the photon diffusion time to get the same answer you've gotten before, basically, or the same scaling anyways, that you've gotten before 2 other times. So now you know how to do this many ways, and that is it for this quick notes on random walk.